Okay, for 4.8 and 4.9, we're going to try something a little different. I'm going to, excuse me, I'm going to teach this from the perspective that I've always used to teach logarithms. And it should match up. We'll see. Come to class and we'll help you make the connections. But we're going to take a look at a logarithm, which is really just an inverse function of an exponential. So we use these to solve exponential functions, and let's go ahead and take a look. So first of all, let's go to arithmetic, and we've actually have quite a bit of experience with inverse functions. An inverse is simply something that undoes what the first function does. So for facts, we have like addition facts. We know that, let's come here. Let me get my pen working. Yeah, we'll go with red. So we know that 2 plus 3 is equal to 5. So we've got sort of two inputs, or two numbers that are being put together and equaling 5. How would we look at this inverse? Well, we take the answer, the 5, and if that's what we ended up with. If we take one of these and we do the inverse operation, so let's take 3, we need to get a new symbol. So we had plus means to add. So somebody came up with a symbol of minus for subtraction. So 5 minus 3 equals 2. So what I want you to see is that in addition, two things are combined to give an answer. With subtraction, that same three numbers just are really moved around. We call this sort of a dance, if you want to think of it that way. So 2 and 3 are dancing together, they produce 5. When 5 wants a dance partner, it chooses either 2 or 3 because it's commutative. But the dance they're doing is the subtraction dance, and that gets us to the other answer. So in algebra, we might think of this as 2 as being like maybe the unknown. And the way we go about solving for x, we would subtract 3 from both sides, right? So what that ends up looking is you take 5 minus 3 equals x. So instead of thinking of maybe doing something to both sides of the equation, that's one thing, it works. But you could also think of it as a dance where, well, this 3 has to come over and dance with the 5, but it's going to be doing the inverse dance. So 5 minus 3 is x, which makes sense because 5 minus 3 is 2. Okay, so I want you to see inverse functions in this light. We have another example of multiplication. So maybe we have 3 times 4. 3 times 4 is equal to 12. So when we go to do its inverse, we take our answer, our 12, and we have it do the inverse dance with either 3 or 4. Let's see, I guess let's go ahead and go with 4. And so we have to have that inverse defined, and we define it as division. So 12 divided by 4 is equal to 3. Okay, so inverse functions. And again, we could have done this with putting in an x for 3, x times 4, or we could list it as 4x off at times, right? And how do we solve this? Well, we've got these two things. So we're going to have the answer, and we're going to divide it by 4. That will give us the third one, right? So we could solve for x in this way, looking at it more as sort of a dance, a reorganizing of the partners. Okay, and yeah, we'll leave it at that. So inverse functions from algebra. So in algebra, instead of being equal to, oftentimes we had a function maybe set up as f of x equals something, right? Or y equals 2 plus x. So let's think about how we would go about solving for x. The inverse function, y is by itself, So the inverse function is going to be y minus 2 equals x. So just going in that sort of steed. And then usually we want to get it back in terms of x and y, so we swap out. But in this section, we're going to focus on logarithms. And so they come from exponentials. So let's just talk about what an exponential function is. We have a base, so this would be 3 raised to some power. And again, if in terms of thinking of exponentials, this would be a 200% increase, right? 300, turn it to a percentage of 300, subtract 100, that'd be a 200% increase. And let's say it's equal to some output. So what we're going to do is we've got the two things, 3 and x on one side equals y, and notice what's going to happen is the x is going to get by itself and the y and the 3 are going to get combined somehow, but we need an inverse sign or symbol for what it means to take an inverse of an exponential. Well, somebody has invented that for us, and they call it the log function, logarithm. And what happens with the log function, this 3, this base, because there's a separate logarithm for each different base. So if this was 2.6, we'd have a separate logarithm for that. And that would go right here. So it's a log base 3, so that's where the 3 goes. And then again, this x has to go to the other side, so the y is going to come in. And notice how we have just solved for the exponent x by doing a little bit of a log dance, just like we did with the inverse function dance, right? Two things are together with one by itself. When you get the inverse, things change. The one that was by itself now has a partner. The one that had the 2 is left over here, and there's an inverse symbol. So here's exponential, 3 to the x equals y. Here's a logarithm, which is an inverse. It will undo what the exponential function does. And we just have to learn sort of the new language for these logarithms. Okay, so log base 3 of y equals x. So notice the output is now the input. The input is now the output. And we'll work through a few examples together. I'm going to skip over this because I should have deleted that one. But basically, any inverse function of y, notice the input, the output becomes the input becomes the output. So those work both ways. And when we take an inverse of a function, we always get back to where we started. So we're starting at x, we're ending at x. And it doesn't matter the order we do it is, if we do the inverse first and then the other function, wherever we start is where we will end up with, because that's the definition of an inverse. It undoes what the other function does. Okay. So subtraction, addition, those are inverses. Multiplication, division, inverses. Exponential, logarithm, inverses. And there's also this special feature that, and we'll talk about this more later. I think in this class we get to to inverse functions a little bit later. So I'm going to skip over this. Again, I probably should have. So let's get to the log dance. Oh, well, we'll do that here. So what I talked about is if we have some base raised to some power equaling some number, that the log dance simply took that statement, took the log, the base remains the base, so we're going to get log base b. The exponent goes over to the other side. So notice every logarithm, the answer to every logarithm question is an exponent. And the output here goes as input into the log function. So that's our log dance. Let's see how we could actually use that to solve an equation like here. We haven't talked yet about what ln means, so we'll do that briefly here. So there is something called the natural number, e to the x. That's a natural number. E itself is equal to approximately 2.7, I think it's 7.1 something, but if you round it up, it'd be 2.72. So we can find that. And so if you have the log base e of something, we use it so often that they said, let's make this shorthand. Let's go and call it the natural logarithm. So we call it ln of x. Okay, so that's the natural logarithm. Why ln? It's coming from the French, and the French logarithm naturel. So in French, they switch the modifiers. So that's why ln is logarithm natural versus the natural logarithm in English. Okay, so how do we solve this? Well, what we first have to do is get the logarithm isolated. So we do that by, what I would do is, since it's negative, let's just add it to both sides. Natural logarithm of 4 minus x. Add the natural logarithm of 4 minus x. And so we get 17 equals the natural logarithm, because when you add that to 0, you get what you started with, of 4 minus x. And what we're going to do is we're going to do the log dance, right? So this is, remember, this is log base e. I'm going to write it that way because that's going to tell me what my base is going to be. So in the log dance, the base stays the base. The answer of a logarithm becomes the exponent, and the input becomes the answer. And then we could subtract 4 from both sides and then divide by a negative to get rid of this, right? So we could finish solving for x here. So we would get, we'll subtract 4, you get e to the 17 minus 4, and then we're going to multiply by negative 1. So I'll just do it this way to get x isolated by itself. When you multiply negative x by negative 1, it becomes positive x, is what we need. Okay, and I've got another example here. So this will be the log dance, but this is with a exponential to a logarithm, right? So think of this as being one whole thing. We've got the log base e, which is ln, and you could write it as such. The output gets put over here, so this is a log dance thing, and the exponent becomes the answer. And again, to finish solving for x, now we do the rest of the algebra. So I'm going to rewrite this just as ln of 8. And we'll look in a little bit. You could actually just plug that in your calculator, or oftentimes we leave it as is. What I would do is while I'm doing this, let's go ahead and subtract. Well, let's do it one step at a time. So subtract 1 from both sides. We get ln of 8, put a parentheses around that, minus 1 equals negative 4x. We're going to divide both sides by negative 4. When we do it on this side, negative 4 divided by negative 4 is 1. So we get x equals natural log of 8 minus 1 over negative 4. Okay. So you see how doing the log dance gets us set up. Just think about it. It's moving those 3 pieces. So we've got a base, an exponent, and an output. when you go from exponential to logarithm, the base becomes the base on the logarithm, the output becomes the input for the logarithm, and the exponent becomes the answer. If we go the other way, you see sort of the same thing. The base of the logarithm becomes the base of the exponential, the answer becomes the exponent, and the input becomes the output, becomes the answer. Okay. Guess I got these slides out of order. We do have two special bases of logarithms. So we've introduced log base e, which is a natural number, and it occurs so often that we simply write it as the natural log of x. So you don't see the e, but you'll have to use it there. And that's one of the buttons you have on your calculator. You have an ln button. So you can, if you want to calculate the natural log of 8, like we had earlier, you could just put ln, put an 8, and you'll get your answer. The other special base of a logarithm is a log base 10 of something. And the reason this is so special is because in our number system, we're doing things by powers of 10, right? 10, 100, 1000. And so there are many scales like the Richter scale for earthquakes. It's a logarithmic scale using base 10. And so going from a 1 to 2 is actually a magnitude of 10 times bigger. Going from a 10 to a 3, a 2 to a 3, each step up is actually 10 times more destruction power because they're doing it by powers of 10. So what they do is with the log base 10, they call that the common logarithm, and they write it as log without a base. Now, when you're studying, you need to follow through. Sometimes in finance, they switch these. They actually have the common logarithm as ln, and there's a few areas of study where they kind of make up their special things, but this is what we do in math. And not that that's how it's always going to be, but just watch however it gets defined. Realize that these things are made up by humans. It's a language deal, so all language is made up, and it's an agreement that we shall do things this way. And when I say this, I mean that this is the log base 10. So if there is no base down here, that implies it's log base 10. It's not that I just forgot to put something there. It's log base 10. And if I put ln, that's implying in our classes that that's got the base of e. And e is a number much like pi, right? You think of pi 3.14, but it has decimal expansion that goes on forever without repeating. Same thing happens with e, but we'll think about it simply as about 2.72. I think it's 2.718 something or something. Okay, so those are our two special bases. And what we want to do is compare the laws of exponentials and the laws of logarithms. So when we do exponentials, right, we had, let's see, how should we do this? We've got like x to the a times x to the b. When we're multiplying these with the same base, we end up with x to the a plus b. Well, with logarithms, we have a similar property, but remember it's an inverse, so it's sort of backwards. And the way it works as being backwards is if we have log, let's call it base c, of something of a, plus the log of some base b, and it's key that these have to be the same base, that's going to be equal to the log base c of a times b. So notice over here the pluses happen inside, the multiplication sort of happens separately out there, and this is sort of the inverse. We have two separate logs being added, gives us one log of multiplication. And again, we could go either way. We can go from this form to this form, or we can go from this form to this form. And we'll work some examples where we do both. Okay, so that's one property. The other property, if you have x to the a divided by x to the b, what we end up with is x to the a minus b. So that's a property of logarithms, or sorry, of exponentials. Logarithms looks very similar, and it's very similar to the addition, but it would be log base c, let's say, because we have to have a base, right, of a, or maybe make it base x to match, but oops, oh, we're not adding. We're going to subtract here. Subtract log base c of b, and what we get is we get a single logarithm base c of a divided by b as our input. And we'll just see that these are properties that we will use to simplify, to be able to solve equations, and sometimes we're going one way, sometimes we're going the other. But we use, these are the three main ones we're going to use. Three, I've got two, right? Here's one, here's two. The third one is if you had x to the a power raised to the b power, that this becomes x to the a times b power. Now with logarithms, what that looks like is log to some base of a raised to the b, and then that's going to become multiplication. So the b is actually going to come down in front and multiply by the log base c of a. Okay, so this one's not as clear as what's going on, but an exponent becomes multiplication. An exponent becomes multiplication. The placing is different, but it's the same process. Okay, so those are the three laws of logarithms that we will be using in this lesson, and they're based off of the properties we used with exponentials. Okay, so let's take a look at this one. Using laws of logarithms, what we're going to want to do is expand this. And so what we see is that there's in the top here, x to the 13th, it's being multiplied by this thing, which is 1 unit, and then in the denominator it's being divided by this. So what we have is we have multiplication results in addition, division is going to result in subtraction. So this is actually going to, what we're going to see is there's three logarithms that are going to come out of this. This times this will be a plus. When we divide, we end up with a minus. So we can just expand this out as the natural logarithm of x to the 13 plus the natural logarithm of the square root of x minus 1 minus the denominator part, natural log of 3x minus 13. Now, we haven't used all the properties. What about these exponents? And actually, when I say these exponents, there's a 13 here. This square root is actually a half power, right? That's really square root of x minus 1 is equal to x minus 1 to the 1/2 power. You're going to have to remember that. So these exponents come down in front. So then you get 13 natural log. I like to write my natural log sort of as a script of x. And that's just, a lot of times this is an input, so it's helpful if you can put parentheses to show where the input is. This one, the square root, is going to become a 1/2 in front here. And then we get the natural log of just, now the square root is gone, x minus 1. And this one has no exponent. It has a 1, so you can bring the 1 in front, but then that doesn't change anything. Natural log of 3x minus 13. So that is an example of taking a logarithm and expanding it out. Sometimes you're given a statement like this, which is 3 logarithms and asked to make it into a single logarithm, and basically you would just take the steps backwards. So those are the things you'll be practicing doing, but it all involves just those 3 properties of logarithms. Change of base formula. You'll see on your calculator you really only have 2 bases. You have the common base log base 10 and the ln log base e. So if you have any other logarithm, and again there's a way to find it, there's a change of base actually on the TI-84, but if you have an older one you might not have access to it. Let's do log base 3 of whatever, 11. Okay, the way you could calculate that is you could calculate it as the natural log of 11 over the natural log of 3. So notice how we're calculating a log base 3 using a log base e. And this is the formula that gets it, is we just have to take the natural log of the input divided by the natural log of the base itself. And the thing is, we'll end up with the same thing if we would have used the common log, but I'm just going to leave it at this. So anytime you have a logarithm with some base, and you need to calculate it, you can do it with the natural log divided by the natural log of the base. I guess that is pretty much what we have. So that should get you started on using logarithms for 4.8 and 4.9. Thanks.